So PCA, known as Principal Component Analysis, okay, is another very nice tool for or algorithm for dimensionality reduction. So if you have a data set which has lot of features, of course, each feature represents a dimension, right? And so these all are the same things: attribute, features, okay, components, dimensions, all are meaning the same thing. Okay, we are using interchangeably one over the other. Okay, so when I talk about attribute, it's like a feature. When I talk about feature, it's also an attribute. It's also representing a dimension, right? So out of, suppose your data has around 30 dimensions or 30 features, your job is to select the most important feature or most important dimensions that matter. Now PCA does exactly the same. So in those higher dimensional space of 30 dimensions or something like that, it identifies which dimensions are the most important. I mean, if you spread out your data in your Cartesian coordinate space, that is XYZ space or more spaces, you try to find where your data is spread out, in which direction the data is spread out. Okay. I mean, I could have given some visual examples like, but you can imagine, how can you imagine? Like, okay. So these are three coordinate systems, and think that you have a balloon. You have a balloon, and inside that balloon, you have lot of what you call this tiny, colorful papers. What you call that? Wrappers. Okay, small, different, nicely colored wrappers inside the balloon, and in each of those wrappers, everyone's name is written. So you can see that all those features are collected inside the balloon. All those features are connected inside the balloon. So all these features are gathered here, right? In a three-dimensional space, right? In a 3D space. So those points are gathered in a 3D space. Now the idea is where you should look into it. Which direction is the most important direction? I mean, is this direction the most important? I mean, if you go along this direction, how many points you visit? See, these data points are already there inside your balloon, right? With names, isn't it? Now my question is, if you suppose go along this direction, then how many data points do you visit? Zero. You visit 0 data points. Okay. But if you visit along this line, yes, you are visiting some of the points. So if you visit along this line, you are also visiting some of the points. If you're going like this, always visiting. But if you go this way, that way, you are not visiting. So the direction is important. Which direction you should move in so that you can capture largest variance in your dataset. What is largest variance in your dataset? The largest variance in your dataset tells where the data has been spread out. Where the data has been spread out. Okay. You are getting the idea, right? I hope. Is it not clear? Or shall we give some other examples? No example. It's fine. Okay. So direction is important. So which direction should I go so that I can capture the largest variance in my dataset? Okay. So to find the direction, we use PCA. Okay. Maybe it is not necessary that you have only one direction. There can be more than one direction. Okay. There can be 2-3 directions also. There can be 4 directions also. Okay. So those 4 directions are the most important directions which can tell a lot about your dataset. What they tell? The first direction is the most important direction. The first direction captures the most variance, like which direction should I go, which represents the most dataset variance most variance in my dataset. Okay. Second direction is the second most important direction. Third direction is the third most important direction. So it is sorted in that way. So first direction is nothing but first component. So those directions are nothing but principal components. Those directions which capture the largest variance of your dataset are nothing but principal components. Okay. The job of principal component analysis is to find those principal components or those directions which capture the largest variance in your dataset. So did you understand? So suppose, and like this example, you have, let us not take this way. So you have this number of points here, okay, with different colors. So there are different features. I'm using different colors to denote, say, different features here. And now, can you tell me, just by your intuition, which direction represents the most, which direction captures the most variance in your dataset, largest variance in your dataset? Yeah. So, is it true to say this one? Right? Why? I mean, we are not seeing whether it is X, Y, Z. We are just checking the direction here. I mean, without this is the direction. We are not checking whether it is X or Y. Just this direction. Why? Because you can see the data has been stretched along this direction, right? So if I go along this direction, I will be able to capture the most variance in my dataset. It can capture the largest variance occurring in my dataset, right? Second important direction can be, you can come across this one. You can come across this direction. If you come across this direction, at least you can capture this part of the variance. Okay. So you can see this is like an elliptical object. This is like an elliptical object, right? Is it correct to say that you can bound this with an ellipse? You can bound with this ellipse. Okay. So if you bound with this ellipse, so you can easily see that if it is an ellipse, there are two axes, right? Like one is major axis, one is semi-major axis, major and minor axis, right? So these are actually two different directions in your PCA. So though these two are the most important components in your dataset. These two directions are the most important one, right? And this is enough. This is enough. So you can rank it lambda. Sorry, you can rank it lambda 1. This is lambda 2. Okay. I mean, we'll see that. Why I'm calling lambda 1, lambda 2, we will know about it. But since it's a direction, we will, and it is a vector. Any vector, what is a vector? Magnitude. Yes, it's having both direction and magnitude. So it's a vector. So it's a v1. And what is the magnitude? Norm, maybe norm. I mean, we will see what is norm and all. But given a vector, this length is just the norm. Okay, that's the magnitude of the vector. Okay. Same way, this is lambda 2, and this is the second most important component. Okay, second most important component which captures some variance in your dataset, right? So this is V2. So you can say V1, V2 are my principal components. Principal components. V1, V2 are my principal components. Okay, V1, V2 are my principal components. Of course, you can have there are, it doesn't, I'm not saying there are no other components. There are also other components. This can be another component. This can be another component, right? So maybe if you are interested, I can assign V1, V2, V3, V4. But the idea is the V1, V2 are the most important parts. The V1, V2 are the most important ones. Mm. Okay, so let us begin again. So you can see that there can be more principal components also, right? Like you can say V1, V2 are, but V1 is the most important one. V1, the first vector we will write in our principal component, is the most important vector or most important principal component which captures the most variance in your dataset. Okay. Next, V2 is the second ranked important vector. Okay, or second most important principal component. V3 is the third most important component. V4 is the fourth most. Like that, you can have as many principal components you can get. But if you want to have the most important features, you can take V1, V2. Okay, because these are the two most important ones. Anyway, so this is the basic idea. This is the basic idea of PCA. Now we will go into deep inside it. Okay. Okay, let us begin. Like, so you can see it's a PCA, that is principal component analysis, is a linear dimensionality reduction technique. Linear dimensionality reduction technique. Okay? Of course, because if you have a lot of features in your dataset, you select only the most important features, right? In that way, you are not taking into consideration the remaining features or dimension. So you are actually projecting from a higher dimensional space to a lower dimensional space. Like say 30 features, you will we will see an example in Python, the breast cancer dataset. In that, you will see that it has around 569 samples of patients' data, and it has 30 features. Each patient has 30 features of the dataset, right? Out of those 30 features, which are the most important features to get? That can be done with PCA. Okay, so you can see you cannot handle all those 30 features. Okay, you cannot handle all those 30 features. Only the most important ones you can handle, right? And PCA will tell which are the two most important ones. Okay, you don't have to work on that. If you just use the PCA command and pass on the data set, it can do it for you. Okay, that's the idea of PCA. But here in this lecture, we will see what are the inner working mechanism of PCA. And then we will go into the Colab and work on the cancer data set. Okay, fine. So you can see it extracts information from a higher dimensional dataset by projecting it to a lower dimensional dataset. Okay, from a higher dimensional dataset, it projects into a lower dimensional dataset in a hope that the lower dimensional dataset can give you a similar set of information as that of the higher dimensional dataset. Not much data is lost when you are projecting it. Okay, I hope that is intuitive. Any issues till now? Any queries? Any queries till now? No. So how can we, now the question is, now that I told you that there are many principal components, V1, V2, V3, V4, now the question is, how can you find those principal components? Okay, how can you find those principal components? So what are principal components? Nothing but vectors. Okay, nothing but vectors. But how can you find those vectors? That's the idea. How can you find those vectors? So turns out, this is the mathematical part here. You could say that principal component analysis is nothing but finding the eigenvectors. Finding the eigenvectors of the covariance matrix. Okay, there is a covariance matrix and you find the eigenvectors of that. What is an eigenvector and eigenvalue? We will come to that. Okay, no need to worry. So basically just remember this fact that principal components are nothing but eigenvectors of the covariance matrix. Okay, covariance matrix, how to create covariance matrix? You have lot of features. You create a covariance matrix based on those features. Okay, suppose you have features like maybe what can I say, like apple. Suppose apple, take an example of an apple. Like what color of the apple? That is color, right? Then what is the size of the apple? What is the texture of the apple, right? And whether it is taste wise, what are the features of that apple, right? Fine. Any other features or anyone want to add? Seedless apple or seed apple? Is anything like that or no? There? No. Anyway, fine. So these are the important features, right? Now you have to make a covariance matrix based on these color and size. Compute the covariance between color and size. Compute the covariance between color and texture. Compute the covariance between color and taste. Start again. Compute the covariance of size and color. Compute covariance of size and texture. Covariance of size and taste. Right? Like that, you create a matrix. Such matrices are known as covariance matrix. I'm just giving an idea. Later it will follow very nicely. Okay, don't worry about it. But when you compute the covariance matrix and find the eigenvector of that matrix, those are nothing but principal components. That's the only idea. And those principal components will give you the ideas along which direction your data has spread a lot. Okay, along which direction your data has spread a lot. Spread a lot means larger variance. Spread a lot, your data has spread a lot means larger variance. The data has spread a lot along this direction, means along this direction it has largest variance. Okay. Anyway, we'll see this. Okay, this line is pretty deep. We'll come to that. Okay. I mean, we should start with the eigenvalue eigenvector so that you guys can understand. Okay, let us see this. We will start with an example of what is an eigenvalue and what is an eigenvector. Okay. So you all know about matrix. Okay. So of course, eigenvalue eigenvector you can only compute for square matrices. Only for square matrix it's valid. You cannot do for any rectangular matrix. What is a square matrix? The number of rows and number of columns are the same. So you can say that this is a square matrix. This is a square matrix. Why? Two rows and two columns, right? Now I am interested in computing the eigenvector and eigenvalue of the square matrix 1, 2, 3, 2. This is square matrix A. Okay. What should I do? What is the definition of eigenvector first? We need to know. Now, eigenvector is nothing but a vector. It's a vector. Okay, but it's a special vector. It's not with just any vector, but it's a special vector. What is special in that vector? Eigenvector of a square matrix A are any non-zero vectors x such that after being multiplied by the matrix, they remain parallel to the original vector. Okay, that's the idea. Okay, so suppose x is the eigenvector. Suppose x is a eigenvector. When it is an eigenvector, when you multiply this vector x to the matrix A, given that the dimensions agree, then now Ax is another vector. Ax is another vector. That special vector will be is parallel to x vector. Now, what does it mean to be parallel to x vector? Same direction, right? But whether it is smaller or bigger, for that also we need a constant, right? Means ax vector, like suppose this is x vector, this is x vector. Now, how ax can look like? Ax can look like this, right? It is parallel to x. Are these parallel to x? These two are parallel to each other? Yes, these are parallel. Now ax is parallel to x. Now this is also parallel to x. This is also parallel to x, right? So therefore, when you multiply x vector to the matrix A, it can either, the resultant vector can be less than magnitude than x or greater than x. Okay, the magnitude can be less than x or greater than x, the length of the vector. So therefore, this ax vector is parallel to x. Okay, fine, but it can be some times of x, some quantity, some scaling quantity, right? Do you agree? Yes, I hope that is intuitive. Is it intuitive? Yes. So you can say that yes, ax is 0.5 times of x. Which is this case? Can you tell me? Is it case 1 or case 2? Ax is 0.5 times x. Case 2. Why? Because almost it is half. Almost it is half. Now, if I tell ax is say 1.3 times x, it is which example? 1 or 2? 1. Because it is more than x. The length is more than x, right? So you can easily see that why, and one more important thing, why x is an eigenvector here. Why x is an eigenvector? Because when you multiplied with the matrix A, the resultant vector ax remained parallel to x. Now it doesn't happen with any vector. I mean, if x is a vector like this, it is possible that ax can be like this. It is possible that ax can be like this. Fine. Yeah. No, I'm telling that there can be vectors x, normal vectors, not eigenvectors. Eigenvectors are special vectors which you multiply with matrix A will give you the same parallel direction as x, right? Now, those vectors which are not eigenvectors, what will happen to them? If x is here, then ax can be here. Are they parallel? No. So this x cannot be an eigenvector. This x cannot be an eigenvector. Okay, what can be an eigenvector if x was something like this? Yes, because x is like this, and if you multiply matrix A, it is parallel. Got the idea? Okay. Now the idea is you understood about eigenvector. You understood about eigenvector. Now, what is an eigenvector? Anyone wants to explain? It is a vector. It is a direction which you multiply with the matrix remains parallel to that direction again, right? Now that is eigenvector. Now I told you it can be bigger or smaller. What is that quantity? The constant quantity, that is lambda, is nothing but eigenvalue. The scaling quantity is nothing but eigenvalue, lambda. So this lambda is nothing but eigenvalue. This x is nothing but eigenvector. And this lambda is nothing but eigenvalue, right? Hope that is clear. Now, the idea is you can see the vector x is an eigenvector of the matrix A with eigenvalue of A, that is lambda. Okay. And you can see why I wrote this equation. To give you an example, to give you a real life example, let us take this matrix A, okay, and let us try to multiply it with an eigenvector. Multiply with this, suppose this is x. 1 minus 1. This is a vector. Okay, this is a vector, right? You multiply this vector with A. Can you multiply? What you do? How you multiply? First row is multiplied with the first column, right? What you get? 1 times 1 plus 2 times minus 1. That is, I did a mistake, is it? It should be minus 1, is it? Okay. Then it should be reversed. Okay, so minus 1. Then check this one. 3 times 1 minus, sorry, plus 2 times minus 1. It is 1 again, right? So you can see, I think I messed it, right? Did I mess it? Let us make it correct. How about a minus 1? Will it be correct? If I put a minus 1, is it correct? No? Correct. How many of you is incorrect? Is it correct? No. Correct. Yeah. Yes. Correct. Okay. It is correct. So you can see that if I take a vector and multiply with matrix A, then this is an eigenvector. Why? Because it is parallel to this vector. It is parallel. Okay. It is parallel. So you can see why this is an eigenvector. And eigenvalue is of minus 1. Okay. So how this is just a very handmade example. Very handmade example. But in technicality, how can you find eigenvectors and eigenvalue? Okay. So what you can do, you can see that Ax equal to lambda x, right? If you multiply x with matrix A, it will be in the same direction as x, right? But it will be multiplied with a quantity of lambda, that is eigenvalue. Now you have this equation. So what you do, take this one on this side, right? So x minus lambda x equal to 0, right? So what you do next, you can take this common out. I hope that is clear, right? Lambda x is nothing but, sorry. Yeah. So lambda x is nothing but lambda times identity matrix times x. If you multiply anything with identity matrix, it is that same quantity, right? So therefore you can see a minus lambda I x equal to 0. And to solve this equation, you have to just use determinant of a minus lambda equal to 0. Okay, and you will get an equation that is known as some polynomial equation, and from that you find lambda. Okay, you will get lambda. And once you find lambda, you can easily find what is x. You can easily find using this equation. Okay. So shall we do an example? Do you want to do an example, or if you want to practically check how to compute eigenvector, we can do, but might not be necessary. Do you want to do or want to do? Okay. So maybe we can consider the same example, no? Let's consider the same example, right? 1, 2, 3, 2. So let us take this example like 1, 2, 3, 2. This is the matrix. Okay. Now what is the idea of eigenvector? What is the idea of eigenvector? what vector I should multiply with x such that it is parallel to x, but I know that it will be scaled, right, by a quantity of lambda. So Ax equal to lambda x, right? And from this, we came back to this equation, right? And I told you that you compute the determinant of A minus lambda I equal to 0, right? Now, can we do that? Okay, so A minus lambda is another matrix. Fine. Do you agree? Okay, can we compute A minus lambda I? Now, what is I, first of all? I is an identity matrix. What is identity matrix? 1 on the diagonals, rest 0, right? So, what is lambda I? You just multiply lambda to each element of your matrix. So, it is lambda 0, 0, lambda, right? Now, this is lambda I, this is A. Can we subtract them? Is it possible? Why? They are of the same size, right? Same square matrix. So A minus lambda is equal to 2 minus 0, 3 minus 0, and agree. Now what you do? What's the next step? You take the determinant of A minus lambda I. Okay. Now A minus lambda I, let me write this clearly. A minus lambda I is just 1 minus lambda, 2, 3, 2 minus lambda, right? Now to take the determinant of A minus lambda I, what you do? Yes. So what you do is this the trick. Okay. I mean, it comes from analysis, but for those who don't know prior ideas about this, I will tell that you take this element, multiply with this one, okay, and then subtract with this multiplied with this. Okay. So what you get from this is when you multiply the diagonal elements 1 minus lambda and 2 minus lambda and subtract and multiply these two, that is 3 into 2. So what you get? Agree? Yes. So can we open it up? So 1 times 2 is 2. 1 times minus lambda minus lambda. This is minus 2 lambda plus lambda square minus 6. Right? Fine. So this is a quadratic equation. Right? Why? Because you have lambda square, then minus 3 lambda, then minus 4. Fine. Now what I told you, to solve this equation, we have to put here. Right? We have to put this equation, isn't it? So what we need to do? Lambda square minus 3 lambda minus 4 is equal to 0. So what we get from here? How can we solve this? Any ideas? So lambda equals to, I hope you remember the quadratic equation, right? Minus b, yes, minus b, there is plus minus root over b square minus 4 a into c, right? Divided by 2a, right? So that is 3 plus minus 5, right? So what if you take plus? If you take plus sign, then 1 lambda 1 is equal to 4. If you take the minus sign, then next lambda 2 is equal to, agree? Fine. So 1 lambda 1 is equal to 4, another lambda 2 is equal to minus 1, right? So these are the two eigenvalues. These are the two eigenvalues. Now, why you have two eigenvalues? So this is the concept. The size of the matrix tells you how many eigenvalues you will have. If you have n cross n matrix A, if you have an n cross n matrix A, it will have n eigenvalues. Maybe some of them can be repetitive, but you will have n eigenvalues. I'm not telling about repetitiveness, but they will have n eigenvalues. Okay. Okay. And similarly, you can have eigenvectors. Okay. Corresponding to each eigenvalue, you will have an eigenvector. Now, corresponding to these two eigenvalues, can we compute the eigenvectors? That's the idea. That's the idea. Now, can we go back to the next page? Or shall I rub this one? Do you want to be in the same page? Or can we go back to the next page? Next page. So you remember, you need to tell me this. Okay. So what is lambda 1? What is lambda 2? Okay. What was A? Is it correct? Sign is very much important. Okay. Okay, fine. So let us compute corresponding to lambda 1. What is corresponding to lambda 1? What is the eigenvector x1? Okay. So what we have, A, if I multiply the eigenvector x1 to A, I should get parallel to x1 but multiplied with lambda 1. Right? Agree? So what I should do, 1, 2, 3, 2 times, let x1 matrix, sorry, vector is say v1 v2, two components, right? v1 v2. So can I write v1 v2 here? And what you have here, lambda 1 is 4 times v1, 4 times v2, is it? Agree? Okay. So what I get from the left hand side, v1 plus and pv1 plus is equal to 4 over v1, 4 v2, right? Can we solve these two equations? How many unknowns you have? Two unknowns, v1, v2. And how many equations you have? Two equations. Two equations in two unknowns. Can you solve it? Yes, you can solve it. Can you solve it now and let me know what is v1 and v2? What is v1, v2? So what you have, v1 plus 2v2 is equal to 4v1. 3v1 plus 2v2 equals to 4v2. So from this, can you tell me what is v1, what is v2? I mean, easily you can find out that from the first equation itself, that what 3v1 is equal to 2v2, right? So yeah, simple. Yeah, v1 is equal to 2v2 by 3. So v1, v2 is the eigenvector where you have v1 equals to 2v2 by 3, right? And v2. So can I take v2 common? So it is 2 by 3 and 1. So any vector of this can be an eigenvector, right? So 2 by 3, 1 is an eigenvector. 2 times 2 by 3, 1 is also an eigenvector, right? 3 times 2 by 3 and 1 is also an eigenvector, right? You got the idea. I mean, if x is an eigenvector, any multiple of x is also an eigenvector. I mean, this is an eigenvector, this is also an eigenvector, 2x. This is also an eigenvector, 3x. I hope you get this idea. Okay. That's how, so eigenvector is not unique. Eigenvector is not unique. Let me remind. Eigenvector is not unique. Okay. If you get one eigenvector, any vector parallel to it is also an eigenvector. Right? That you saw it right now. Because you saw it from here, that you can see that this is an eigenvector. And V2 you can take anything. V2 you can take anything and still it will be an eigenvector. So it is not only the eigenvector, it is a eigenvector. Okay. Fine. Now can you compute same for lambda 2, x2? X2 say this is V3, V4 maybe. So x2 for x2, what you need to do? Ax2 is equal to lambda 2 x2, right? So what is lambda 2? Minus 1, right? So x2 is minus v3 minus v4. Can we solve this? So what you get here? V3 plus 2v4, 3v3 plus 2v4. This is coming out to be minus v3 minus v4. Can we solve this? So basically from the first equation, you can see 2v3 plus 2v4 equal to 0. So v3 equals to minus v4, right? So what you got from this is basically v4 you can take it common and minus 1, 1 is the eigenvector. So this is x2, this is x1. So this is another vector x2. Okay. So these are the two eigenvectors. These are the two eigenvectors corresponding to the two eigenvalues, lambda 1 and lambda 2. Okay. And you can check also. You can check and you can see that why this was the case here. Okay. I hope this is clear. So now you understand how, given a matrix A, you can actually find the corresponding eigenvalues and the corresponding eigenvectors. Okay, because and how you have to solve it. I hope that is clear. Okay, so now you know, given a matrix, how to find eigenvalue, how to find eigenvector. Same idea we will be using in PCA. Same idea we will be using in PCA. Now, how it will be useful in PCA? In PCA, the matrix you are seeing here, A, here, is nothing but the covariance matrix. Is nothing but the covariance matrix. Agree? So it is the covariance matrix made up of from the features of your data set. All the features you have, you make a covariance matrix based on those features, and the covariance matrix, you compute the eigenvalues and eigenvectors. Those eigenvectors will give you the principal components. And choose the most important first two principal components, and those are the most important principal components. And that's how you decide and do the data reduction, dimensionality reduction. Are you able to understand the full part or logic of PCA so far? Okay. Okay. So let us be back now. So shall we start with this? Yeah. So you can see this is an example of a flower data set. Okay. Where you have all these samples. All these samples are there. And what we do here, these are the features for each sample. For each sample, you have these 4 features. That is sepal length, okay, sepal width, petal length, petal width. And these are the features, okay. You can see this 145 sample has sepal length of 6.7, and you can see most of the flowers are almost similar, 6 point something, okay, but not exactly same, varying somehow, okay. Sepal width also, you can see how they are varying. Petal width across samples and petal length also. Okay. So this is kind of the data set. I gave you an example. You can perform PCA on this. Okay, you can perform PCA on this. Anyway, so this is just an example I showed you. What you mean by features and how you can compute correlation for that. Okay. Mathematically, I think it is better if we can do some mathematical idea first, or is it better to look into the theory first? That's what I am thinking. What do you prefer? Maybe theory first. Maybe theory first. Now that you know the what you call the basic idea of PCA, we will learn a bit more finer details of PCA. Then we will just see a mathematical example how to do a PCA analysis, eigenvalue and eigenvector of covariance matrix. And then after looking into that, we will go to Python example of breast cancer dataset, where we will see how to handle PCA in reality. Okay, using commands. Fine. Okay. So where you can apply PCA, that's the first question. So the idea is data visualization. So when you are working on any data related problem, okay, the challenge is dealing with this sheer volume of data and the variables and features that define the data. Okay. What are the features? You will have a lot of data and as well as lot of samples, and together with you with lot of data sets, you will have lot of features. Each sample will have lot of features. So how to deal with those? Okay, it's a higher dimensional problem. To solve a problem where data is the key, you need extensive data exploration. Fine. To understand how the variables or the features, I told you, variables, attribute, features, dimensions, all are the same. Okay. So we use this interchangeably. Okay. So when I tell you how the variables are interrelated or correlated, that means how features of your data samples are correlated. That's what I am trying to tell you. And understanding the distribution of few variables or understanding distribution of few features of your data set. So since you have larger number of variables or dimension along which the data is distributed, of course, visualization is going to be a challenge. If you have 30 features or 30 dimensions, how are we going to visualize that? those 30 features. One way is like you can do two features visualize on a 2D plot or 3D plot. But that's so many details, so many plots. Using so many plots, how can you make a interpretation from that visualization? Okay. If you make a visualization, is not only for the sake of good plot, but what information can it provide? If it is a good plot, but it is not a good figure or good plotting figure, but it is not able to give you any information or intuition behind that, then it is not a good visualization technique to deal with. So PCA, so visualization can be a challenge here and almost impossible because you are dealing with such high dimensional data. So PCA can do that for you because since it projects the higher dimensional data into lower dimension by projection. Okay. So how you do that? Like dimensionality reduction. You select the most important features of the data. How will you know most important features of the data? You compute principal components, that is eigenvectors of the covariance matrix, and it will give you the directions which are the most important ones, and select that. Okay. Also, one most important thing about PCA is, of course, data visualization, and one most important thing is speeding up your machine learning algorithm. This might be covered in your second semester. Okay, this might be covered in your second semester. But PCA you can directly use to speed up any machine learning algorithm. Okay, but because you are reducing the dimensionality of your data, so of course the training and testing and validations, all those things which would have been going through in lot of features will now be going on only in selected features and most important features, thereby powering and speeding up your machine learning algorithms. Okay. Is it okay till now? Intuitive? Okay. So since PCA's idea is dimensionality reduction, you can leverage that to speed up your ML algorithms, testing and training time, since your data has a lot of features. Okay. Fine. So the idea is simple. You take a data set with many features and you simplify the data set by selecting, you simplify the data set. Remember these keywords. Simplify this dataset. You simplify this dataset by taking only the most important features. Only the most important features. And those are nothing but principal components. Fine. So what are these principal components, which you already know about? Okay, I already told you. So principal components are the key to PCA. They represent what is underneath the hood of your data. Means if you have a bigger data set with a lot of features and you don't know which features are the most important, PCA will tell you which are the most important features. Okay, that's how PCA is important to you. In layman terms, when the data is projected onto lower dimension, assume say 3 dimensions from a higher dimensional space. The 3 dimensions are nothing but 3 principal components. Those 3 dimensions are nothing but 3 principal components. Okay. That captures or holds most of the variance. Okay, if the data is spread along in one particular direction, that means your information is most prominent in those directions. Your data has most amount of information in those directions. If you don't go along that direction, then you are missing out the important chunk of data. If you don't go along the direction of most variance, you will be missing out the important pieces of your data. So it is important to go along a particular important direction. And how to find particular important direction is through eigenvector analysis. That's the plan. PCA, for those who are from math background, might be understanding this more clearly, that PCA is nothing but an orthogonal linear transformation. You are just performing a linear transformation on your data. Okay. And each of your principal components will be orthogonal to each other. Each of your principal components will be orthogonal to each other. That means perpendicular. Okay. So these all details is okay. I mean, on a wider audience, I just told you that a deeper aspect of this. If you go deep and deep, the story is huge. Okay. As usual, since principal, what is a principal component? It's a vector. It's an important vector. Any vector has direction and magnitude. So you can see principal components therefore have both direction and magnitude. Okay, now you can relate whatever I told you before, isn't it? Okay. So the direction represents, see, the most important aspect of this, the direction represents, not a good, yeah. Direction represents the across which principal axis data is mostly spread out. It's most important line. Most important line. So the principal component has direction and magnitude. Now, what is the significance of the direction of the principal component? The significance of the direction of the principal component is it is such a direction that it captures the most variance in your data set. Okay, where the data is mostly spread out and has most variance. Okay, and what is the magnitude? If a direction is so much important, why we are only worried about direction and why magnitude is also computed? Magnitude also has a role. Okay? Magnitude signifies the amount of variance. Okay, the principal component direction will give you in which direction they are spread out, but the magnitude signifies the amount of variance or amount of spreadness. Okay, fine. So you can see the principal components are a straight line, and the first principal component hold the most variance in the data, and therefore the first principal component is the most important direction and represents where the data is mostly spread out. Okay, fine. Agree? Any issues? Any issues so far? Okay. Okay. So this is something, last line is a bit mathematical, which I don't want everyone to understand. But each subsequent principal component is orthogonal to the previous one. Okay, they will be perpendicular to each other. Okay, fine. So let us see this idea here before we dive into more. Like you can say, like this is Ci. This is a principal component I am writing. Okay, Ci is the ith principal component. Okay, and these are your features. These x1, x2 up to xn, these are your features. Okay, now this principal component direction is built. This principal component direction is built with all the features in mind. Okay, all the features in mind, x1, x2 up to xn. Okay, fine. So how you compute variance? So variance of features, this is a feature. So variance, how to compute the variance? I hope you already know about this formula, right? You compute the mean, and this is xi, the first variable, xi minus x bar, the square, sum of squares. You take the square of each ith feature or variable, and you sum along all the variables and take the average out. Agree? Okay, this is the variance. This is the variance. So what does variance signify? The variance is a measure of how far a set of numbers are spread out. How far the set of numbers are spread out. Fine. I'm trying to give you an intuition of what is spreadingness mean. Or what do I mean if the data is spreading out a lot more? Okay. Fine. So next we come to covariance. I told you the eigenvalue and eigenvector of the covariance matrix is nothing but the principal components, right? Are the principal components, right? So therefore you need to know how to construct a covariance matrix. Okay. So covariance of any two variables x and y, you not need to know what is the covariance between x and y, the variable. So you need to know how these two variables change together. Okay. So how, if these two variables, you want to know how they go hand in hand. It might be that if x increases, y decreases. X is inversely proportional to y. If x increases, y decreases. If x increases, y also increases. So to know this trend, you can compute covariance of x and y. Okay. How you can compute covariance of x and y? Same thing. Instead of the squared product, you can take difference from the mean of x bar multiplied with difference with the mean of y bar and take the average out. Take the average out. Take the average out. Okay. This is how you can construct covariance of two variables x and y. Now this is a covariance. This is covariance. But then what is covariance matrix? You understood? This is defined as covariance of two variables x and y to see how they change together. Right? Agree? Fine. Now I want to understand what is a covariance matrix. What is a covariance matrix? Okay, because the principal components are nothing but eigenvectors of the covariance matrix. Principal components are nothing but eigenvectors of the covariance matrix. Okay, not covariance. What you understood so far is covariance. So what is a matrix? So covariance matrix is a square matrix, n cross n square matrix, where each element of that matrix is a covariance element. Okay. So you can say, like, suppose you have x, x, y. You construct these features. Till now you have only two features, isn't it? X, y, right? So you create x, y, x, y. Then x, x. I think biology students can understand this table, right? X, x, right? X, x. So covariance of x comma x, right? X, y. So covariance of x comma y, right? Then you come to y and x. So covariance of y, covariance of x, right? Understood? No? And you take y and y. So covariance of y, y. Any issues here? Any issues here? Fine, no? Okay. Now, what special do you see in this matrix? Biologists use these for genes, right? Use this for genes. I think to refresh my memory, Mendel's, yes, XX is female, XY is male, something like that, right? Crossing, yeah. So now, okay, fine. Now you created a covariance matrix. So this is a covariance matrix. Now I'm asking the audience. Okay, so yeah, did you understand? Did you understand what is so nice about this matrix within this gap? What is nice about this matrix? I would like to ask mostly from CSDA and DSCS. What do you see nice about this matrix? Shall I color? Yeah, shall I color it for you? Let me color. Yeah. What do you see nice about this matrix? Hmm? Color. Yellow color. Okay. Hmm. What is like special about this matrix? Flat. Square matrix, huh? Square matrix. But yes. Yeah, it has information about all the covariance of all the features. In that way, it is correct. But what is special about this matrix? I mean, it is so special that it is the heart of PCA. I mean, not many talk about it, but due to this, you don't get eigenvalues to be complex. Eigenvalues can be complex also. Let me remind you, eigenvalue doesn't need to be real. Eigenvalue, there are matrices where, let me come back. When you applied this square root, right? When you applied this square root, indeed, understood? If you apply the square root, can the thing inside the square root go less than 0? It is possible. B square minus 4AC can be less than 0. You will have complex roots. We have complex conjugate roots, right? So it can be less than 0. In that case, your eigenvalues are complex. So for a real data set with real entries, what does complex eigenvalue tells you? It tells you nothing, right? Nothing it will tell you. Can you measure complex numbers? Is 3 plus 4i greater than 3i? You cannot measure complex numbers, right? So why in PCA, as I told you, that eigenvalues is more important, eigenvectors are more important. Why in PCA you are getting real eigenvalues? If PCA is so nice algorithm, it should be giving real eigenvalues, right? It should be giving real eigenvalues. Therefore, the method is so nicely known. Now my question is, now you understood that eigenvalues can be complex also. So now my question is, the moment eigenvalues will be complex, PCA fails. PCA will fail because the moment eigenvalues will be complex, PCA fails, right? Why? The complex eigenvalue doesn't give you any information how your data is spread out because you cannot compare complex numbers. So my idea is what prevents in PCA from the formation of complex eigenvalues. Take covariance. Huh. No, what I am telling is this matrix is a matrix, right? Square matrix. Now we are computing the eigenvalue of the square matrix. Now my question is why there are only real eigenvalues? Why not complex? That's my question. Okay, shall I spill the bean? Okay. So observe carefully the covariance matrix M. It is a symmetric matrix. It's a symmetric matrix. That means if you take the transpose of M, what is the transpose of M? The rows you make it columns, right? So what is this row? Like what will happen to the covariance? Sorry, the symmetric matrix. The row I am transferring here, then covariance of covariance of x comma y, is it equal to covariance of y comma x? Yes, because it's nothing but interchanging these two products. So therefore this matrix is nothing but the same as this matrix. M and M transpose are the same. So M is equal to M transpose. So therefore M is a symmetric matrix. And symmetric matrix can only have real eigenvalues. It cannot have complex eigenvalues. That's a property of the symmetric matrix. So therefore you see how PCA is built up and is working only due to the covariance matrix. If the covariance matrix was not symmetric, eigenvalues maybe turn out to be complex and PCA would have failed. So this is the mathematical background of PCA, why PCA is working, why PCA never fails. Okay. So this is, depth. Okay. So I just want you to give you an understanding that there is something known as a covariance matrix. So when you are talking about PCA, don't undermine covariance matrix. Okay. That's the boss. That's the boss. Okay. So due to covariance matrix, PCA is successful. Fine. So let us come to an example now. Enough of our ideas. So, okay. Let us take these two features. Okay, example in action. So you can see a lot of this is not the end. It is going on. It is going on. So this is how I made a plot here. Like you can see feature 1 and feature 2. Okay. Feature 1 here and feature 2 here. Okay. So these are the two features. And I'm plotting those elements here. Okay. In a just a scatter plot. So you can see that the data sets, the data points are being distributed, isn't it, across the graph? Points are distributed across the graph. And at some point, you might be clueless about how to segregate them easily. Now, if you see this, your first idea is along which direction my data is spread out. Okay, not a good color, is it? Along which direction? Along which direction my data is spread out. Okay, so we don't know. Yeah. So that's the idea of PCA. When we apply PCA, it will give you a direction where your data is spread out. Okay. To help you out of the trouble here. So you can see, so when you compute the covariance matrix and find the eigenvector direction, it gives you these two directions. It gives you these two directions. Okay. So you can see that is this is the first principal component here, and this is the second principal component, right? So when you have to detect and recognize thousands of samples, you would require an algorithm to sort this out, and PCA does exactly the same. So how this is PCA is being used in your ML algorithms to help you fix this problem. Okay. So this is a category. We will take an example, like take apple category. You have spoiled apple, one category, branched quality apple in one category. Okay. In the second category, two different categories of apples. Fine. So basically, this is the idea here in PCA. So first of all, I told you about standardization, right? Did I talk about standardization? Okay. But there are many types of standardization. What are they? You can subtract by mean and divide by sigma, right? One of the popular standardization tools, right? Z-score, Z-score normalization, and min max. Yeah. Okay. Okay. So the one of the most important aspect is like we standardize. Okay. We standardize our variables here. So standardize this range of continuous variables. Okay. So yeah. Okay. 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 So this is the idea. So first of all, the most important aspect of PCA is to standardize the variables. Okay. So you have to perform the standardization. Okay. That's the most important step and the first step. Then of course, on the remember very importantly, the data set you have, you just don't pass it and create covariance matrix. You standardize the data set, and to that standardized set, you apply the covariance matrix. Okay, you construct the covariance matrix based on the standardized data set, not on the raw data set, on the standardized data set. Okay, in Python also you will see that we'll be doing it. Okay. So then after that you compute the covariance. After that you compute the covariance, okay, to identify correlations. Compute eigenvectors and eigenvalues from that covariance matrix, okay. Why? Because to identify principal components. Fine. Then you come back and decide the feature vectors. Which are the most important principal components I have to take? As you know, they will be automatically sorted out for you. The first principal component will be the most important principal component. The second will be the second most important principal component, and so on. It will be automatically ranked for you. Okay. Now you have to recast that data along those principal component axis. Okay, that this is nothing but from here to here is nothing but known as coordinate transformation. Okay, nothing but coordinate transformation. Fine. Because you will be in some XYZ space, but now that will be converted to some V1, V2 space. This is the principal or V3 space. Okay, this is the principal component coordinates. Is it clear? Right? So this is known as data like what do you call this? Coordinate transformation, right? If you go from one coordinate system to another coordinate system. Okay. So you were in previous coordinate system of XYZ. Now what you do, identify the most important features. Those are the principal components and recast the data along those principal components. So that's like a coordinate transformation. Okay. So these are the parts. Okay. Now let us see. So step one, as usual, is the standardization. Okay. So when you do the standardization, the range of the variables is calculated and standardized in this process. Okay. To analyze the contribution of each variable equally. Okay. To analyze each variable equally. This you know, x minus mu by sigma, right? This standardization we already learned in the previous class. Agree? So you can see this. These are the features F1, F2, F3, F4. What are the features? Large size apples, rotten apples, damaged apples, small apples. Okay, and these are your values for different samples. Okay. Now the idea is how we can construct covariance matrix from this data set which has 4 features. Now it is a higher dimensional data set because there are 4 dimensions. Now suppose this 4 dimension is big or huge. Of course it is huge. We cannot understand this 4 dimensional space beyond our understanding. So we have to recast it or project it into a lower dimensional space. That is either 2 dimensions or 3 dimensions, right? So you can see I computed the mean for F1, F2, F3, F4, and the corresponding standard deviations, right? Then what I will do, I will standardize. So what I did, I applied the standardization procedure to each of them. Agree? To each of them. I mean, F1 you do, for F1, for this element, you do 1 minus the mean of F1 minus sigma of F1, right? Agree? Now to 5, what you do? To standardize it, sorry, 5 minus mean of F2 divided by sigma of F2. Agree? Agree? Okay. For F3, what you do? 3 minus the mean of F3 divided by sigma of F3. Similarly, for this one to standardize, 1 minus mean of F4 divided by sigma of F4. Right? So same thing we are doing here. Same thing we are doing here. And after standardization, you get these quantities. Can you see what has happened so far? Previously, you were having this data set. Nice looking data. Sorry. This nice looking data set. Integers. All were integers. Then when you standardized, there will be division. There will be subtraction. So guarantee you will see fractions or decimals, right? So that's what you are starting to see here. So you see after standardization, what you got here. Okay. So you can see that after standardization, you got these elements now. Fine. And you have applied it to all elements. You have applied it to all the elements, right? Agree? So this is now the standardized data set. And we will work on this data set, not the original data set. We will take the original data set, standardize it, and we will work with the standardized data set. Fine. Now we will see this data set only in further slides in processing. Okay. Now we have to create a covariance matrix, right? So how many features were there? 4 features, right? F1, F2, F3, F4. So I am writing it down here, F1, F2, F3, F4, right? And how I am creating a covariance matrix? Covariance of F1 and F1. That is nothing but variance. That is nothing but variance. Okay. Try to understand why covariance of x comma x is just variance of x. Okay. From the definition I gave you today, just try to understand why covariance of x and x is just covariance of x. Okay. So you can easily see xi minus x bar, xi minus x bar. Those two terms will be multiplied and they will be squared. Therefore, it is nothing but variance, right? So you can see, and F1 and F2, see F1, F2 here, F1, F3 here, F1, F4 here. Are you seeing how this matrix is being constructed? Okay. So F2 also, how you will do? F2 combine with F1 to get F2, F1. F2 again combine with F2, variance F2. F2 combined with F3, covariance of F2, F3, right? Fine. So one property again, it is a symmetric one, right? It's a symmetric one. How nicely you see the diagonal. The diagonal is consisting of all the variance. Okay. Diagonal is consisting of all the variance and it is symmetric, right? Fine. So let's see, compute the eigenvalues. Now think of this matrix as a matrix, M or A matrix. This is an A matrix, right? Which you computed eigenvalue of a 2 by 2 matrix. How you will compute? You will do determinant of A minus lambda equal to 0. So you have to subtract minus lambda through each of the diagonal elements. And that's exactly what you are doing here. That's exactly what you are doing here, right? You are subtracting lambda everywhere. Fine. Now this is the matrix. What is this matrix? This is A minus lambda. A minus lambda, this is the matrix. Fine. Now you can compute. Now these eigenvalues you can compute. Okay, it is difficult to compute eigenvalues of a 4 by 4 matrix. Okay, you can use Python for that. Okay, we can use Python for that or any other programming language. And suppose we got the eigenvalues. Let us see the eigenvalues. Okay, from here, can you compute eigenvalues? How many eigenvalues will be there? Why? Yes, it's a 4 by 4 matrix. So there will be 4 eigenvalues. So lambda 1, lambda 2, lambda 3, lambda 4 will be there. So what are those values? We'll see next. Okay. So you can see these are the eigenvalues. Okay. You can see 1, 2, 3, 4. And they are listed according to the importance automatically. Okay. So you can see once you have computed this eigenvector component, define eigenvalue in descending order for all variables, and you will get a list. You will get a list of principal components. Okay. Now you can see which one is the most important element here. This one is the most important element. This is the most important element because it's the first principal component. The first principal component holds. Why it is most important? Because it holds input information about the most spreadness of the data. Okay, or the most variance of the data. Fine. Okay. So the eigenvalue represents the principal components, and these components represent the direction of the data, right? So you can easily see this. And yeah, same things are written here. So these finally, let us see this line. Finally, these principal components form a line of new axis for easier evaluation of data, and that's what we will see. So instead of these 4 dimensions, what we can do is take the first 2 most important principal components for your analysis, right? So what you will do, you will take only these 2, right? These 2. So what information does it give? It gave you the information that these are the 2 eigenvectors, E1 and E2, okay? And these are the most important directions because they capture the most variance in your data set, and these are the principal components. These are your principal components. Okay. So you can see what I have done. I have taken lambda 1, lambda 2 and corresponding eigenvector E1, E2 of this data set. Agree? Fine. So you can see how instead of taking the 4-dimensional space, I am taking only 2 dimensions. Why I am taking only 2 dimensions? Because they are the most important ones. Now, who told they are the most important ones? Because they capture the most like spreadness of your data or most variance in your data set, right? So therefore, you take these 2 directions here. Okay. Fine. Now the second step is recast the data along those principal component axes. It's just like coordinate transformation. I told you. Now you have new directions. That is eigenvector 1, eigenvector 2. Now you have to recast your data along those principal component directions. Okay. So still now, apart from standardization, you have not made any changes to your original data set. To your original data set, you have not changed anything because you have only performed standardization. Isn't it? Anything else did you do with the data set? No, nothing we have done. So you have just selected the principal components and formed a feature vector. Okay. And yet the initial data remains the same on their original axis. Fine. These steps aim at to the reorientation. Okay. The reorientation of the data from their original axis, to the axis of principal components. How to do that? You can say like standardized original data set multiplied by the feature vector. That will be giving you the final data set. Okay, that's how we are casting our original data set along the direction of principal components. Okay, by multiplying the original data set with the feature vector. If you multiply your original data set with the feature vector, your data set is already being cast in the direction of principal components. Okay, this might take a bit of experience to understand why this works. Okay, but you can start with some examples. Okay, take one vector and put a matrix multiplied with that vector and see where it transforms the new vector to. Okay, by doing some experiments, you can confirm or convince yourself that when you multiply the feature vector to this matrix, it will be casting your data set onto the direction of principal components. Okay. So after standardization and covariance matrix computation and all these things, this one is the most important step. Like casting, this is just like a coordinate transformation. I mean, you are coming from this coordinate axis. You are coming from this XYZ coordinate axis to some other coordinate axis of principal components. Okay, some other coordinate transformation. So this is your original data set, and you're casting it here. You're casting your data set onto this principal components. Okay, fine. Okay. So you can see this is the standardized data set already taken before. This was our feature vector. Okay, so what you have to do? Multiply the data set with the feature vector. Fine. So what you get? You see this is the transform data set here. And you can easily see which are the most important features here. That is the large size apples and the rotten apples. Okay, so out of all the 4 different kinds of features, these 2 features are the most important ones. I mean, even though you don't have to take all 4, you can bear with all these 2 only. Of course, you will lose some efficiency in this process. Why? Because you are leaving out 2 more important features, 2 more features, not important features, 2 more features, but you are only choosing the 2 important features here and eliminating the other 2. So some loss will be there, definitely, but it is enough for you to understand this higher dimensional data set. Okay, that's how dimensionality reduction works. Okay, you will be losing some information, but enough to make you understand about this higher dimensional data set. Is it fine so far? So you can understand how this is inner piece is working of PCA, right? This inner piece, how the calculations actually works in PCA. Okay, fine. So this was all about PCA in your math examples, like how PCA actually works, what is inside PCA, how to compute covariance matrix, eigenvalue, eigenvectors, all these things inside insider of PCA. Now, after this, we'll transform into the, we'll go to Python example. Okay, we'll consider a real data set, okay, and see how PCA is working. Of course, like these are some applications just to see. Definitely, I urge everyone that when you go to new semesters, try to understand how PCA can be useful in machine learning. How PCA can be useful in machine learning. Okay, because PCA is useful in machine learning to speed up the algorithms. Okay, to speed up the algorithms. If your machine learning algorithm is working very, time-consuming process, PCA will be one of the important aspects. Okay, so in the same way, SVD, singular value decomposition, is also one of the most important algorithms here. Okay. In healthcare also, you can see, we'll see the data set example. We'll see the data set example in Python. Okay. So PCA helps to resize an image. So what you can do is also there are image pre-defined image datasets where you can apply PCA also. So that I am not going to discuss in this class. I might discuss towards the end if time permits, but you can search what are the predefined image datasets in Python available in scikit-learn library, okay, and try to apply PCA in those image datasets. Okay, that will be interesting. So you can see stock data forecasting, fine. To analyze patterns, when you are dealing with a high dimensional datasets. Okay, PCA can help you find patterns because you need to find the most important features in your dataset, right? So these are all for you to understand, but most of you we will be learning in deep in next semester. Okay, like you can see, predictive algorithms will be coming next semester. Okay, what kind of predicting algorithms can be understood from this? We already know about this, that it increases performance of ML algorithms. So increases visualization. It increases visualization. It helps reduce noise. Okay, fine. So disadvantages is also like PCA is difficult to interpret sometimes. Sometimes difficult to interpret. In rare cases, you may feel difficult to identify the most important features even after computing the principal components. So, most important thing is interpretation. If you are working on a data set, you need to know, is it possible? Is it plausible? Like, is it giving me the information I want or no? Okay, like you in cancer data sets, you want to know how many cancer patients are spread out. You don't want to know how many non-cancer patients are spread out. Okay, so therefore, if you are studying those data sets, non-cancer patient data set, it is not of any use. You want to understand which patients of cancer are relatable, are like having what can I say, impact on different variables, like say like they were exposed to high radiations, or which factors, or they were under UV exposure. There are many factors. So you have to make interpretations. Fine. Unless you do that, there is no use. So yeah, you may face difficulties in computing covariance and covariance matrices. Okay, it is useful because it is not that hard, because nowadays you don't have to manually type these matrices. Just one command can help you make these matrices for you. Okay, fine. So these are the ideas, and yeah, I think yes, yeah, this is something important also. PCA, remember this. PCA can be applied to both ordered and unordered attributes. Okay, PCA can be applied to both ordered and unordered attributes, right? And most importantly, PCA can handle sparse data and skewed data. PCA can handle sparse and skewed data. Remember, when we were having skewed data, I told you what kind of techniques can we use to understand that skewed data. So we thought that mean, median, mode, okay, which one is better? Okay, we came to know that median is better, right? Like for a central tendency measure, right? But the idea is like if you can apply PCA also to them. If your data set is skewed, if your data set is sparse, having lot of empty elements or zeros in your matrix, PCA is not affected. PCA can be useful in it. Okay, so you can see PCA is a very powerful tool. Okay, can handle sparse data, can handle skewed data, can handle both ordered and unordered data sets. So you can see multidimensional data sets, of course, it can handle more than 2 dimensions by reducing the problem to 2 dimensions, okay, or 3 dimensions, depending on the problem. Maybe the third feature is also equally important, right? You can use the principal components as inputs to multiple regression and cluster analysis. Okay, multiple regression, more about regression you will be coming to know in the next semester, like in second data analytics course. I mean, predictive analytics, something like that. So in comparison with wavelet transforms, this is also important. We also learned about wavelet transforms. We learned about pyramid algorithms, right? So we saw that in comparison of wavelet transform, PCA tends to be better at handling sparse data, whereas wavelet transforms are more suitable for high dimensionality problems. Okay, so can be asked like how, like wavelet transform and PCA, which one is better in what aspects? Wavelet transform is useful when you have a higher dimensional data sets, whereas PCA can work very nicely even if you have sparse data sets. Wavelet transform might fail when you have sparse data. Okay, so these are the ideas. So let us go to an example, shall we? Python example, right? Hmm. Okay. Okay. So I hope that this is visible to last, not visible. Okay. So we'll begin. Hmm? Okay. So first of all, we have to load this dataset. You can see the dataset module in scikit-learn provides access to several preloaded datasets that are commonly used for testing and learning machine learning algorithms. So this is already a preloaded dataset. This I am not taking the dataset from anywhere else. I am just taking it from sklearn module. Okay. This includes dataset like iris, digits, wine, breast cancer datasets. And we are taking only this example. However, you can play with these three other ones. I suggest you guys to go and check what this iris dataset does, what this wine dataset does, and all. Okay. So load breast cancer is a function, okay, that loads this breast cancer Wisconsin diagnostic dataset. I think this is US based dataset. Okay. So we import this function from sklearn.datasets module in Python. Okay. So this you can see is used to load the breast cancer dataset, which is commonly used dataset for classification task in machine learning. You will see why this dataset is so nicely, but for that you have to wait till the end. Okay, why, to understand this line, why it is commonly used for classification task in machine learning, you have to wait till the last figure of the lecture today. So once the dataset is loaded, it can be used for training and testing your machine learning models. Okay, so the load breast cancer will give you both labels and the data. Okay, you can see to fetch the data you need to call dot data, and to fetch the labels or the features you have to call labels.target. Okay, understood that, no? So this we'll see, don't need to worry. So you can read these writings after the command just to make you a bit more comfortable what is happening. Okay. Okay, fine. So now that we have imported it from the sklearn module, let us say breast equal to load breast cancer. Okay. And this is how the data set is. Okay. And you are printing the shape of the data. You are printing the shape of the data using dot shape. So breast dot data dot shape. When you do that, it gives you 569,30. So it tells you the shape of the data set. Okay. It tells you that it has 569 rows and 30 columns. Fine. Okay. Then to know the number of like breast dot target dot shape. Why we do dot target? You can see to fetch the labels, you use dot targets. So we wanted to know how many labels are there. If you want to know how many labels are there in your dataset, you need to use dot target. Yes. So you see breast dot target, best dot target, right? And then shape. So how many labels are there? So you can see the output is 569 comma 569 comma. So how this 569, what is 569 comma means? It's just a vector. It's just a vector. Okay, just a vector. Okay. Now what are the features? So you know that what is the size of this data set? 569 rows and 30 columns, right? So you can see that there are 30 features here. There are 30 features here. Now what I am trying to do is I am trying to understand what are the features. What are the top 5 features, right? So you can see breast dot feature names. Okay. So I am trying to print the feature names, first 5 feature names from the breast cancer dataset. So you can see it printed out the names of the features: mean radius, mean texture, mean perimeter, mean area, mean smoothness. Okay, these are the first 5 feature names out of the 30. However, you can print all 30 of them. So I will give you this Colab file. What I ask you to do is change this column 5 to column 15, column 20, column 25, column 29, column 30, like that, and see how it is printing the number of features. Okay, fine. Okay. So you can see what are the target names, means what are the label names. What are the label names? Means to each sample what category it is assigned. Either it is assigned malignant or benign, right? So you can see when you do breast dot target names, it is giving you malignant and benign. These are the two labels we are assigning. These are the two labels. Okay. So this is the explanation again. Like you can see 569 comma is just one label for each of the 569 samples. 569 comma is just a vector of length 569. It's just a vector. We will see the difference. What is the, some of you might have confusion. What is the difference between 569 comma and 569 comma 1? Okay, many definitely have that question, right? What is the difference between 569 comma and 569 comma 1, right? We'll see that, no need to worry. Okay, so fine. So you can see this breast.data, when you do, these are the feature values or the numeric measurements from breast cancer biopsies, and these are 30 features per sample. And how many samples are there? 569 samples. There are 569 samples, right? Okay. And you can see that these target names are malignant or benign, right? Fine. You can also do .descr to know the description of the dataset. I suggest this. I have not done here, but I suggest you try this. Okay, DESCR. Okay, fine. So you can see the dataset contains information about breast cancer tumors, including various features such as radius, texture, perimeter, as well as a target variable indicating whether the tumor is malignant or benign. Okay. So you can do this like breast.data, you can store it in this variable breast underscore data. It will, the size is just 569 rows and 30 columns. Okay, the same thing, nothing else. 569 is the number of samples or patients, 30 is the number of features that is obtained from the measurements from your breast cancer biopsies. Each row corresponds to a patient, and corresponding to each patient, what are the different features for that particular patient. Okay. So I hope you understood how the dataset looks. I hope you have the visualization in mind. Yes. Till this point, any issues? You understood how the dataset is looking like, right? Anyway, so these are still repetitive things. Fine. You can see I'm using the shape command here, dot shape. And it is giving you 569 rows and 30 columns. Okay. Of course, you don't need labels here. Okay, you don't need labels here, but just for understanding, I have shown you this like best or target. So you can see, you will see a number of zeros and ones. In the data set, they have not written malignant or benign. Okay, they have given you 0 for malignant tumor, 1 for benign tumor, non-cancers. Okay, so these are the just the what do you call that? Are you able to understand this or any issues? No, right? So in the data set, when we will be printing, you won't see benign or malignant. It will be either zeros or ones. Okay, that's the idea. So you know when a 0 is there, it is malignant. When a 1 is there, it is benign. Okay, fine. So okay, breast labels dot shape fine 569 comma, that's we already have seen. Now, like you can see that when I do breast labels column 40, so it is giving you how to each sample what category or label it has been assigned to. So it is a series of like zeros and ones. So what is zero? We saw zero, yeah. So zero is malignant. So you can see lot of first like 40 elements are all like malignant, but in some places there are benigns. Ones are like benigns. 3 ones are there, so they are benigns, and there is one more one here which is benign. Okay. So it prints the first 40 elements of the breast labels array. It's the label. Let me remind you, it's the label. You already understood the labels are just 0 and 1, that is malignant and benign. Okay, fine. So don't worry about this column 40, it's just a slicing notation. I hope you will cover, or I don't know if it is already covered in your, so it will be covered. So don't worry about this, but try to understand the overall idea. I mean, this column 40, these small details you can later understand for sure, but understand how the things are working on a general perspective. Okay, so as I told you, let us see the difference between 569 comma and 569 comma 1. Okay, so what is 569 comma? It's just a 1D array. Okay, when you are considering 569 comma, it's just a 1D array. So you can see its shape is 1 dimension with 569 elements. But when you do 569 comma 1, when Python returns the shape as 569 comma 1, it is a 2D column vector shape. That means 569 rows and 1 column. To understand more about this, let us consider a tiny example. So you can see the first example here, np.array 1, 2, 3. Okay. So I have created this array here 1, 2, 3, and I am trying to understand the shape of ARR. Okay. So what I do, ARR.shape. So when I print it, it is giving 3 comma. When I print this, it gives 3 comma. Okay. But at the same time, when you do like np.array individualistic square brackets like 1, 2, 3, okay, and you compute the shape, then you can see it is 3 comma 1. Okay, then you can see it is 3 comma 1. Okay, so what's the difference? So you can see this explicitly creates a matrix like structure with 1 column. Okay, so it depends how you feed into your array. Okay, so you can see that the first example you just did 1 comma 2 comma 3, but in the second example you just put some square brackets inside and you consider them as a block. Okay, so more about this you will be learning, I mean detail in that, but I'm just giving you a tiny, because this might be small confusions in these small concepts here. Okay, so you can see this is useful. Why this is useful? I mean, why we are bothered about 569 comma and 569 comma 1. Okay, so this comes from a perspective that many machine learning algorithms need a particular kind of input. Many machine learning algorithms need a particular kind of input. Okay, that's what is explained here. So this is useful when you need to do matrix multiplication or pass data into ML models expecting 2D inputs. So some algorithm might need 2D inputs. Okay, in those cases, like you can see scikit-learn TensorFlow usually expect 2D arrays instead of 1D. Okay, so they expect something like 569 comma 1 instead of just 569 comma. So therefore we have to transform that 569 comma to 569 comma 1. I hope that is clear, right? Why we are doing this, right? Because the input some machine learning algorithm take is a 2D input vector, right? So therefore you cannot pass 569 comma because it's just a 1D. It's just a 1D, but 569 comma 1 is just 2D. Okay. Fine. So therefore 569 comma is just 1D. Some functions reject it. Okay. And 569 comma 1 is 2D, and it works nicely for your ML algorithm inputs. Okay. Fine. So you need to reshape it. So remember, when we did that, we got the output as 569 comma, right? When we did the labels dot target, do you remember? Breast dataset dot target dot shape. When we did that, we got the output as 569 comma. We forgot. This one, breast labels dot shape is 569 comma. It's a 1D. Now, since these machine learning algorithms are taking data sets as 2D, that is 569 comma 1, we have to reshape. We have to reshape our data to convert from 569 comma to 569 comma 1, right? To do that, you have to use a function known as reshape. Okay. To do that, you have to use reshape. So you can see this like np.reshape. np.reshape. You are reshaping your data here. Okay, reshape breast labels. Which one you want to reshape? Breast labels, and in which format you want to reshape? Yes, I want to transform 569 comma to 569 comma 1. Okay, so you are writing it here. I need in that format. So when you do that, you already have it. Now can we print and look into it? So when you print labels, the for first 40, you can see these are in square brackets as we did before. Okay, and you can see these zeros are malignant and one are benign. Okay, you can see easily those things are printed here. Fine, so far. Okay, okay, fine. So next is like what we are trying to do is like we are trying to concatenate the features and labels. Okay, why? Remember carefully that your data set and features are two different objects here. Like for data you were doing breast data like dot data, and for labels you were doing using dot dot target. For labels you were doing dot target, right? So now these are two different things. Okay, now what I want to do is something like this. I mean, I can explain it here a bit. So now what I want to do is like this is the feature, right? So this is this. So these are 569 here, okay, and these are 1, 2, 3, so on up to 30, right? So these are these are like radius, the perimeter, the smoothness, many factors here from biopsy, right? Now, corresponding to each patient here, this is the first patient, you have whether it is 0 or 1, malignant or benign, right? This is the label. Now, what are we doing here? We are concatenating these two. Means we are merging these two together. That means we are the same data set here, all these 30 features here, 1 to 30, but the labels is also concatenated into the data set. Are you understanding? 0, 0, like 1, fine. So that's what concatenate will do for you. You're concatenating the data and the labels. Which sample is assigned which tumor? Agree? The first patient is assigned malignant or tumor. We now want to know. So to know that, we are concatenating that. Simple as it is. Okay, nothing else. That we are seeing here. You can see np.concatenate breast data with labels. Breast data and labels you are concatenating. Fine, right? Okay. 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 So you're concatenating the breast data, which has 569 rows and 30 columns together with the labels. Okay, whether it is benign or malignant. That's what we are doing here. Okay. Okay. So you can see that we are concatenating the breast data and labels here. Okay. Fine. So you can see the above line is joining your features, that is the breast data, and your labels, that is malignant or benign, into a single combined array, into a one combined array. So final breast data will have everything, every information. What information it has? It will have all 569 rows. It will have all 30 features. As a last column, it will also have whether it is malignant or benign, right? But finish. Why is so serious? Okay. So you can see why you have to believe me, right? So you can actually print the size of the new data set, right? So what we did, one extra column was there. You remember 30 features were there, right? Now you added concatenated and added one more column. The size increased by one, right? So you when you do final breast data dot shape, you see 569 rows and 31 columns. From 30 columns, it went to 31 columns, right? Now, how the first five rows looks like? Of course, not a good way to print this. This is not a good way to print. Okay. So of course we want to see, but I want to show you something like this last part. You see, this is the last entry, 0.00 e to the power plus 00. It's just 0. Okay. And this is just 0, 0, 0. So these are the 0 and 1s. But I will show you in a data frame. Don't worry. Uh, don't worry about this. Okay, let us import pandas for this so that we can see in a tabulated manner. Okay, so import pandas and pd.data frame. We made this to a data frame. Final breast data is a data frame now. Okay, now breast data set is nothing but a data frame. Okay, is a data frame consisting of 31 columns, right? So when you are printing this, when you are seeing this, you see how many it has. Okay, you can see the last parts for that. Yeah. So you can see the last column here, right? You can see, so you can see these are the data sets 0 to 568. So 569 rows, fine. And these are the features 17.99, 10.38. All these are different features obtained from biopsy for each of your patients, from each of your patients. And what we did, it will go on like that to the end, that is 30, right? From 0 to 30, it is going. From 0 to 29 are the features. What is the last column? Labels. What is 0? and what is one benign, right? So I hope you understood this idea, right? Okay, fine. So you can see here features. So what are the features actually? I mean, I want to know what are these 30 features all about. So what are these 30 features? You can see these are the mean radius, mean texture, so many things here. Okay. Worst symmetry, worst fractal dimension. Okay, fine. So okay, fine. So what we can do is like, yes, one more important thing notice here is it is not a good looking data set. Why? Because these features are represented by 0, 1, 2, 3 up to 30, right? Yes, these features are not mentioned clearly. So what we want to do is to write down the features it actually means so that it is easier to visualize this data set, right? So for that, you can do something like this. You can say np.append like features comma label. So you will assign these labels to each of them. Like you can see, it has now assigned these labels, mean radius. Okay, when you use the label, you can see mean texture, mean perimeter, so on till the last. And the last is just the label. But still there is a problem. Maybe we don't want 0 and 1. Maybe we want, see, I am continuously asking what is 0 and 1. So why we need to do? We can just put the, just replace 0 with malignant, 1 with benign, right? Okay. So this is the idea next. Yes. Since the original labels are in 0, 1 format, you will change the labels to benign and malignant using dot replace function. I mean, you want to replace 0 with malignant, replace 1 with benign. So that you can do with dot replace function, right? So here you are learning about some new function along the way. Along the way, some new functions which you might not have heard. Okay. Okay. So you can see how we are doing this. Like you can see breast data set. This is our final data set. You replace 0, dot replace 0 with benign and replace 1 with malignant. Okay. Don't worry about syntax and all, but just remember about the logic here used. Replace 0 with benign. Did I do wrong? I did the wrong, right? You can correct it. Okay. So replace 0 with malignant and replace 1 with, replace 1 with benign. Yes. So yeah, that would be correct. Okay. So try to do that. I think I mistakenly wrote the other way around. Okay. So you can see now when you do the dot tail, the last 5 elements, last 5 rows, right? When you see this, you can see that now instead of 0 and 1, it is printing benign and malignant. Okay. So how to do that? Previously it was 0 and 1. What you used? Dot replace function to do that, right? Now, what I want to know is in my data set of 569 samples, how many benign samples are there, how many samples are benign, and how many samples are malignant. It is indirect way of saying that can we understand the occurrence or the frequency of malignant or benign. That you can do with value counts function. Okay, that you can do with value counts. It will count in the whole data set how many labels are occurring for how many times. Okay. You can see this is the method value counts in pandas used to count the occurrences or frequencies of each unique value in a series. Okay, use each unique value in a series, right? It will return how many times benign or malignant, okay, appear in the label column after your replacements, right? So you can see dot value counts. This is the final data set we have, breast data set, right? You do value count function to this. And it gives you, this is the label malignant, 357 samples are malignant, 212 samples are benign. And does it add up to 569? Yes, you can carefully see that they add to 569. So you can see that you are not missing out on any sample, right? Fine. So visualizing the breast cancer data set here. So as usual, we understood the first most important. So we played till now. We have played with the dataset. I mean, how many rows are there? How many samples are there? How many, like we constructed, we saw what are the features, what are the name of the features of your data set, mean radius, mean smoothness, perimeter, all those things from biopsy. And we saw how many labels it has. It is either assigning to each sample with a benign or a malignant. Yes, we concatenated that, right, into a final set, right? And to that final set, what we did, we saw the labels were not coming in. So we used, yes, yes. And then we saw that last columns was having the label of 0 and 1. 0 was malignant, 1 was benign. So what we did, we used replace function, saying that wherever 0 is occurring, you replace that set of zeros with malignant, and whenever 1 is occurring, you replace it with benign, right? So you got the full data set now. So that's what we have done so far. Okay, and we also saw how many occurrences are there for benign and how many occurrences are there for your malignant cancerous cells, right? So we saw that there are 357 malignant sample cases and 212 benign sample cases, right? Now, okay, this is all about playing with this breast cancer data set, right? Now, the first step of PCA begins, right? What is the first step? That is standardizing the data. Okay, this is standardizing the data. So you can see visualizing the breast cancer data, you start with standardizing the data since PCA's output is influenced based on the scale of the features of the data. Okay, so don't worry about it. As we have already discussed, we standardize, so we'll standardize. So normalize the data before feeding it to any machine learning algorithm. So this is why standardization and normalizations are so important. Okay. So what we do here to apply normalization, we import this standard scalar module from here, from the sklearn library. Okay. You can see it from here, like standard scalar we are applying here. So try to explore more about standard scalar. Why we are using standard scalar? Did I not cover this in standardization? Did I not cover? Okay. Try to remind me. Okay. These things I forget. I should take some chunks in future class. Okay. But anyway, it's good that you have seen it here in practice. So you can see you will import standard scalar module from the sklearn library and select only the features from the best breast dataset you created in your data exploration step. So previous from till here, whatever you have done so far is just like data exploration. Okay, so some things known as like exploratory data analysis. We are not calling it EDA, exploratory data analysis now yet, because you have not learned yet data visualization. Okay, you have not yet learned about data visualization. The moment you learn about data visualization, you plot it. All the things what you have done so far is referred to as exploratory data analysis, EDA. Okay, fine. So okay. Okay. So why are we using LOC here? So anyway, you can see from sklearn.preprocessing, we imported standard scalar. Now my question to you is, why are we using LOC? Remember, I told you about LOC and ILOC. So what is LOC? What LOC is doing? Hmm? Okay. Hmm. Name of where? Like, okay. Label. Name of the label. You can select the full code. Good. So you can see why LOC is used here, right? So then you can see like we have used this standard scalar dot fit transform. So here it is normalizing all of your feature elements. You saw there were a lot of numbers, right? There were a lot of numbers in your data set. Do you remember? No. There were a lot of numbers. Now you see one is 1479. One is 1479. Okay. So this is the fact. This is the fact. For each of the features, you have to normalize it. For each of the feature, you have to normalize it. One of the feature, it is ranging from 1479, but the next feature is suddenly coming to 0.11. Okay, so for each column, you have to find the mean, subtract the mean, divide by the sigma, right? Same as I told you in the apple case, rotten apple and those example cases. Okay, fine. So you can see now you have standardized this. Okay, you can see this standard scalar, what it does, it standardizes feature by removing the mean and scaling it to unit variance by dividing by sigma. So that x minus mu by sigma, that is being done by the standard scalar function here. Unless you want to find mean, use a for loop, you can still do it. How you can do it without using standard scalar? Use a for loop over all the features, compute for all the columns the mean and sigma and subtract and do it. But instead of all those for loops, you can just use standard scalar. Which what it will do, standard scalar from each of the features, from each of the column of the features. It will take the mean of that feature, subtract the mean and divide by the sigma. That is what standard scalar will do. Fine. Okay. If it is not that clear, maybe we can cover this in a separate class, like what is a standard scalar can do. Okay, what it does and what is kind of syntax for that. Okay, all those things in detail. I mean, remind. Anyway, but the idea is the same. Like you can see, standard scalar standardizes the feature by removing the mean and scaling to unit variance. This means after transformation, each column will be standardized to mean 0 and variance 1. Okay, that's what is what we have learned in normalization, right? Now, this is what standard scalar does. Now, what does fit transform does to your data X? Okay, so fit transform is two things. Fit learns the mean and standard deviation from the data, and transform applies the scaling. Okay, there are two things. Fit transform. So fit learns the mean and standard deviation from your data, and transform applies that scaling. Okay. So anyway, this is a bit heavy. This is a bit heavy. I mean, to understand what is going on in detail. But the catch from this is standard scalar is going to do the normalization for you. Oh, sorry, the standardization for you. That is x minus mu by sigma, standard scalar. Okay. And why we are doing like this? That's my question to you. I mean, just within one line, the code is finished, right? Because it does for all the 30 features. It does that for all the 30 features. In this one-liner code, standard scalar, it computes the mean. How many columns we have? 30 columns. It does compute the mean of each column and sigma of each column and standardizes automatically for each of the 30 columns. That's how powerful standard scalar is. It doesn't matter to it how many columns it has. It will do automatically check the mean and the sigma for each of the columns. So that's what this fit and transform you can see. It automatically learns the mean and standard deviation from the data. Okay. So I urge that you understand these 3 lines when you go home pretty much deep. Okay. Because this is where the PCA first step starts. Okay. Standardizing your data set. Okay, I urge everyone to learn these 3 lines carefully. Okay. Now, X is our data set, right? Now we want to understand what is X, how it looks. So we took shape. So it is the same 569 rows and 30 columns, right? It's the same 569 rows and 30 columns here. Okay, but it is a standardized data set now. Okay, so shape remains same, but the values have changed after standardization, right? Let us check whether the normalized data has a mean of 0 and standard deviation of 1 or not. So for that, what we do, np.mean x and np.standard deviation x. If you do that, it prints the mean and the standard deviation for the dataset x. You can see it is giving minus 6.8 something 10 to the power minus 17. That is practically 0. Okay, that is practically 0. 10 to the minus 17 is practically 0. And you can see the standard deviation is 1. So the mean is 0 and the standard deviation is 1 after standardization. Okay. Is it fine? So you know that standardization has been applied. and a new data set X has been created, which is representing the standardized data set. Why it is standardized data set? That also we have proved, because the mean is 0 and variance is 1. Yes, standard deviation is 1. Okay, so you can see like how many features also it has, 30 features. Okay. I don't want you to show the for loop now. Anyway, no worries about that. Anyway, forget about the looping. Just see this again. So we are again coming into the same features. So feature 0, 1, 2, 3 up to 29. Okay, that means 30 features. Here we have not concatenated the labels. Mind you, here we have not concatenated the labels. This is a new data set, standardized data set. Okay. Now this is the critical part where we apply PCA. Okay. Let us read this. So you can see our data set was a 30-dimensional data set, right? Because it represents 30 different variables or 30 different features from the biopsy of the from the patients, right? Now what it will do, from the 30-dimensional data set, you want to project it onto 2 dimensions. You want to project that 30-dimensional data set and reduce it to the most important 2 dimensions. This is our idea. I mean, you can project it to 3 dimensions also. Okay, you can even project it to 4 dimensions also. Okay, but up to you how many dimensions you want to reduce it to. Okay, that input you have to give into PCA function in Python, right? So you can see you will use the sklearn library to import the PCA module. Okay, and in the PCA method you will pass the number of components you desire. Okay, I want to what do you call? Any issues? I want to project that 30-dimensional space into 2 dimensions or 3 dimensions. But I have to give to PCA module, right? How much dimensions or how many principal components I need. So it will give you all 30, but first important are the first values are the important ones. You know, the first one is the most important one, right? So you can see from sklearn.decomposition import PCA. Okay, so you can see here PCA breast is equal to PCA n components equal to 2. N components equal to 2. That means I am telling that you project that 30-dimensional data set onto 2 dimensions. I want only out of those 30 features, I want only the 2 most important features. I want 2 most important features out of the 30 features. That is what I am telling here. PCA bracket n components equal to 2. You can still do n components equal to 3 if you want 3 most important features out of the 30. But I have done 2 here. I suggest you try 3. Okay, n components equal to 3. So you can see dot fit transform. We will see what this fit transforms does. Okay. Okay. So you can see sklearn is scikit-learn, fine. What is decomposition? It's a module inside scikit-learn that contains algorithm for dimensionality reduction. Okay. So a lot of new things are coming on here. Okay. I understand it's difficult to digest, but this is the way you have to, I mean, get introduced to new things. This is the only way you can get introduced to new things. Okay. Now this is a module. What is, just have bit of patience. I understand it's already one. So bit more. Last line. So what is decomposition does? It's a module inside scikit-learn that contains algorithm for dimensionality reduction. Okay. And matrix factorization like PCA or SVD. SVD, PCA, all these things are matrix decomposition. Okay. You will be learning in subsequent semesters about this. But sometimes what happens is, if you have a matrix, sometimes it is better to write that matrix as a product of different matrices. Okay. I mean, matrix A you are writing as a product of A1, A2, A3. Okay. Then you will see suddenly that the algorithm has increased its accuracy when you pass that decomposed matrix. Okay. So therefore, therefore, this is the motivation why decomposition is used. Okay, decomposition is used. Okay, decomposition is used because it has all the algorithms useful for dimensionality reductions. PCA is one of them. So therefore, you are using sklearn.decomposition and you are importing PCA from it. That's the story. That's the story. Okay. Anyway, and you can see it decomposes the highest dimensional data into few meaningful components or the features, and those are nothing but principal components, right? Those are nothing but the principal components. Okay. Fine. So fit transform again does two things. I already told you that fit learns the principal components, transform projects X on those components. Okay, that is fit transform. Okay. So this is, this 5 lines holds the whole PCA session. Okay, I suggest please try go home and read the importance of each of them line by line. Okay, what is fit transform? What is n components equal to 2? What happens if I change n components equal to 3? What happens when I change n components equal to 4? Okay. Fine. So, but before I stop, I just want you to show the picture of this before we stop. Now, I told you that we converted the 30-dimensional data set into 2 dimensions. Okay, and I am printing those dimensions here: principal component 1 and principal component 2. Nothing but features. Okay, so you can see the. Let me see. Yes, this is the legend. You can see the red ones are the benign and the green ones are the malignant. Okay, and you can clearly see how this data is linearly separable. When we call a data is linearly separable, if you can pass a boundary line such a way that it separates two classes of the data set, right? So that is known as the decision boundary. Okay, and that is how your support vector machines and introduction to machine learning starts. Okay, so like just I will tell you tiny motivation before stopping. So what we saw here is like there were blue chunks here, okay, and there were red chunks here, right? So what you can do is just pass a boundary line to this, and this is known as the decision boundary. Okay, this is known as the decision boundary, and people from DSCS and those like can properly appreciate like it is represented by a line equation W transpose X equal to 0. These are weight vectors in your machine learning algorithm, the weights you give to each of the nodes. Okay, and you can predict. See, if it is equal to 0, what does it mean? On this side, it can be less than 0, and on the other side, it can be greater than 0, right? That's how continuity happens. From negative, you slowly go to 0, then go to positive. That's how the number line is, right? So therefore, what machine learning does, it finds whether this W transpose X is less than 0 to predict whether this is blue or not. Okay, and if it is greater than 0, it tries to see whether this is red or not based on these two conditions. So this you will learn more how this is how machine learning classifies whether blue is blue or red is red. And what happens if something like some falls near to the boundary, then it is very difficult to classify. Okay, when it falls, some element falls near to the boundary, then it is very difficult to predict which class it falls to. Okay, so this marks the start of machine learning. This marks the start of machine learning into how machine learning can classify different features, okay, and predict different features, right? So this is how it starts. Anyway, my job was just to give you an idea of PCA and how you can apply PCA into a real-time data set and see how it can convert a 30-dimensional feature to 2 dimensions, okay? So this was the idea. So I suggest I will share this collab, okay? So try to learn, try to fiddle with values. Wherever I have done 2, you try to put 3 and check what new output you are getting. Okay. And what decomposition does, what sklearn does. Okay. What are different types of datasets available. So I showed you a tiny part, but you know how these parts are connected to different other areas. Now you should try to explore those parts. Okay. Okay.